If you've been following modern AI, it can feel less like a structured field and more like, you know, a thousand technical terms just flying at your head.
Oh, absolutely.
Uh,
Agents, RAG, embeddings, guardrails. It's a lot.
it feels like pure chaos. And it makes it almost impossible to figure out what any company is actually trying to sell you.
Well, that feeling is really the cost of just incredibly rapid innovation. Every week there's a new acronym, and you need some kind of framework to see how it all fits together.
Exactly. And that is our mission today. We are going to try and impose a little bit of elegant structure on that chaos.
We're doing a deep dive.
We're diving deep into this idea of an AI periodic table. It's a conceptual tool that organizes all these different bits and pieces of AI, much like the one you remember from chemistry.
And it is such a powerful mental model. I mean, you're not going to find this in a textbook. Not yet, anyway.
Right.
But if you understand the structure, you can decode basically any AI architecture, any product pitch you see.
So you can see which elements are being used, how they react with each other, and maybe what's missing.
Crucially, what might be missing. It turns that information overload into a structure you can actually use.
Okay, so let's set the scene. There are two main organizing principles for this whole table.
That's right. It's all about the rows and the columns. The rows, which we can call periods, represent levels of complexity. You start at the bottom with the basics and move up.
And the columns.
The columns are families, group things by what they do. Their core capabilities. So you have families for things like retrieval or validation or the models themselves.
All right, let's unpack this. We have to start at the beginning. Row 1, the foundation.
Row 1 contains what we call the primitives. These are the absolute atomic elements that can't be broken down any further. If it's not one of these three, it's a combination of them.
Okay, first one. Group 1, the reactive family. We have prompting.
Right. The prompt is just the instruction you give to the AI, but it's in the reactive family for a reason.
Why is that?
Because it's volatile. Like in chemistry, you change just one word in that prompt, and you can get a completely different, almost unpredictable output. It's control, but it's super reactive.
That makes perfect sense. Okay, moving over to group 2, the retrieval family. We find M.
M is for embeddings. And this is, a really crucial concept. It's about turning language meaning into math.
Turning a dog chases a frisbee into a string of numbers.
Exactly. And the genius part is that similar meanings get similar numerical values. So the AI can search based on the idea, not just the keyword.
Which is why it's the absolute backbone of the retrieval family. It's how AI systems remember and find things.
Precisely. It's the primitive for finding context. Now let's jump over to group 5, the models family, for our third and final primitive, LG.
The large language model, the LLM. This is the brain. ChatGPT, Claude, IBM Granite.
Yep, the foundational capabilities. And to stick with our chemistry analogy, we like to think of these as the noble gases.
Why noble gases?
Well, because they're stable, they're foundational. They kind of create the environment where all the other more reactive elements can actually operate.
Ah, I see. So they don't react much themselves, but they enable every other reaction to happen. That's a great analogy.
It helps it stick.
So just to be clear, row 1 has only 3 things. Prompting, embeddings, and LLMs.
That's it. Everything else we're going to talk about is just built by combining those 3 in different ways. It really simplifies things.
Okay, so if those are the atoms, that brings us to row 2, where we start building molecules.
Exactly. Row 2 is for compositions. These are elements that need multiple pieces to actually work.
So back to the reactive family, G1. Below prompting, we now have FC for function calling.
Function calling is when the LLM decides it needs to take an action. It needs to call an outside tool or an API before it can give you an answer.
Right. So asking for the capital of Italy is one thing.
That's just the LG element.
But asking it to book me a flight?
Now it needs function calling to connect to a booking tool. It's the family evolving from just instruction to actual real-world action.
Okay, group 2, retrieval. Underneath embeddings, we have VILX.
Vector databases. This is a really natural composition.
Because embeddings are useless if you can't store them.
Right. You need to store and search millions of them and do it fast. Vector databases are built specifically for that kind of semantic search.
This next one feels like the glue holding enterprise AI together. Group 3, orchestration. RG for RG.
Retrieval-augmented generation. RAG is, it's absolutely central to almost every company's AI system today.
And it's the definition of orchestration because it's coordinating all 3 primitives.
That's right. A question comes in, the system uses M and VidX to retrieve context. It then uses that context to augment the prompt, the PR.
And then finally, the LLM LG generates an answer that's grounded in that retrieved data.
It's like letting the AI check Wikipedia before answering the test question.
And notice there's a gap in row 1 for this group. Orchestration only shows up here in row 2.
Well, yeah, you can't orchestrate a single thing. It's an emergent property. You need the pieces first.
Right. Okay, next, group 4, the validation family. This is where we find GR, guardrails.
The safety net.
The safety net. But I have to ask, if guardrails are just filters you apply after the fact, aren't they just sort of masking potential underlying safety issues with the model itself?
That is a really critical point to make. And you're not wrong. Guardrails don't fix a model's core safety, but they are a necessary layer of defense at the system level.
How so?
They're runtime filters. They stop the inevitable slips. They enforce that the output is in the right format, that there's no inappropriate content, that it follows company policy. You need both core safety and system-level defense.
Fair enough. Okay, and wrapping up row 2, in the models family, we find
Multimodal models.
the LLMs that have broken the tyranny of text.
That's a good way to put it. Yeah, they can process audio, images, video, as well as text. And this one element is completely changing how we think about user interfaces.
Moving beyond the keyboard.
Ex-
So those 5 function calling vector databases, RAG, guardrails, and multimodal models, that's pretty much what's powering most of the AI you interact with today.
For now, yes. Which takes us to row 3.
Right. Once you've composed your systems, the next step is memory, scalability, and autonomy.
Let's follow that reactive family down. So from prompting and function calling, we now get to egg agents.
This is the move toward true autonomy. You're not just asking a question, you're giving it a goal.
Precisely. Agents use this internal loop. Think, act, observe. It breaks a big goal into smaller steps, executes them with function calls, sees what happens, and then decides the next move, all on its own.
That's a huge leap, from simple instruction to automated execution. Now, what about G2, retrieval? We're talking about time scales of memory here.
Yes. So we had M for encoding meaning and Venx for storing it. Now we have EBHE, fine-tuning.
This is about deep specialization, long-term memory.
You're taking a base model and training it intensely on your own data, like a company's entire legal archive or code base.
So you're baking that memory directly into the model's weights.
You are, which is why it's a much slower, more permanent form of memory than just a quick vector search.
So G2 shows us 3 time scales: instantaneous encoding with M, searchable storage with VX, and deep permanent memory with FFeat.
A perfect synthesis of that column.
Okay, orchestration family, G3. We have FW frameworks.
This is the plumbing. Platforms like LangChain that tie all these different elements together so you can actually build and deploy a full system.
And next door in validation, G4, is art red teaming.
The adversarial side of safety.
This is where you are actively trying to break the AI.
Yep. Prompt injection, jailbreaks. You're stress testing the system's defenses to see if you can make it leak data or do something it shouldn't. Unnecessary evil.
And finally, for row 3, in the models family, we get SIMUM, small models.
Highly optimized, specialized models. They're distilled from the bigger ones. They're faster, much cheaper to run.
And some can even run locally on your phone. It's about practical deployment.
Exactly.
Okay, this is where it gets really interesting. Row 4, the emerging frontier. This is the stuff that's happening right now.
Very much so. It's all still rapidly evolving.
So the extreme end of the reactive family, G1, becomes multi-agent systems.
So we're moving beyond just one agent with a plan to multiple specialized AIs all collaborating.
Like a digital project team.
That's the perfect way to think about it. You'd have one agent for research, another for drafting, and a third that just critiques and edits. They work together to solve really complex problems.
Wow, okay. Group 2, retrieval. We find synthetic data.
As models get bigger, we're actually starting to run out of high-quality real-world data to train them on.
So we're using AI to make training data for AI.
It sounds a bit circular, but yes. It's about generating massive amounts of reliable, high-quality data to keep pushing the models forward. It's critical for future scale.
Let's jump to validation G4. We find IN for interpretability.
This is really the cutting edge of safety work. Because if an AI makes a critical mistake, we have to understand why.
Not just that it happened.
We need to know why. Interpretability is about building tools to peek inside that black box, to actually map concepts to specific neurons. It's about finding the causality in there.
And finally, the models family, G5, gives us T thinking models.
These are, hands down, the smartest models available today. And the key feature is that they do not answer immediately.
They actually take time to think.
They use complex reasoning processes, like building an internal chain of thought. That's part of their architecture. They're slower, they're more expensive, but they are just exponentially smarter.
And we should point out that gap in row 4, G3. There's no emerging orchestration paradigm yet that goes beyond the frameworks we already have. It's an empty box.
It is, which tells you where future innovation needs to happen.
Yeah.
But look, the real power of this table isn't memorizing it. It's using it to predict things.
To model any AI system as a reaction between elements.
Exactly.
So let's run a couple of reactions to show how this gives you, a critical thinking superpower. Let's start with the most common one, the RA chatbot.
Okay. A company takes their documents and runs the M element embedding to turn them into vectors.
Then Vex to store those vectors in a database.
When a user asks a question, it runs RG, array, to retrieve the relevant context. That context then augments the PR, the prompt.
Which is then sent to the LG, the large language model, to generate a grounded answer.
That's the core reaction. But, as we said,
Smart companies add the draw element, guardrails, to wrap the whole thing in safety filters.
it's not a complete system without that validation. Okay, reaction 2. The agentic loop. This is autonomy.
We start with AG, the agent, and give it a complex goal. Plan a weekend trip to Rome.
The agent then breaks that down and uses FC, function calling, to talk to external tools map APIs, reservation systems.
It observes the results from those tools and loops back. Think, act, observe, over and over.
And that entire complex loop is built and deployed using FW frameworks to provide the plumbing and stability for it all to run.
So any AI product you see, from the simplest chatbot to the most complex system, it fits on this map.
Every single one.
So here's the challenge for you, the listener. This is your new superpower. The next time you see an AI pitch or a demo, pull up this table in your mind.
Map it out. What elements are they using? What reactions are they running?
And are they missing something critical, like guardrails or red teaming?
And are they maybe over-engineering it? Are they using a big, expensive thinking model, a T, when a much cheaper, small model, Shima, with a little bit of RAG, would do the job just as well?
This framework gives you the confidence to call that stuff out.
It really does.
So what does this all mean? When you boil it down, this AI periodic table gives you a categorized, linked view of all those chaotic terms we started with.
It turns that mess of ideas into a single decodable and, predictable structure.
It's the essential shortcut to really understanding mechanics under the hood of any modern AI system.
And this is the knowledge that changes you from just being a passive consumer of AI news into a critical evaluator of the technology itself, which raises a final, maybe provocative thought.
Go on.
Given how important AI is becoming in, every field, do you think we'll eventually see a version of this AI periodic table plastered on school classroom walls right next to the real one?
That is definitely something to mull over. We will leave you with that thought. Thank you for joining us for The Deep Dive.